Welcome back. In the last lecture, we started the momentum flux. We needed to understand fluids because you wouldn't have had a background in fluids. We looked at first the shear stress and how shear stress can be considered as momentum flux. And then we looked at the most important characterization or a very important characterization of fluids in terms of its rheological properties, typically a tau shear stress versus shear rate graph, the various types of fluids and the two major types of flows. This is what we have seen in the last class. Today we will start analyzing the flow and of course, I don't have to tell you how important flows are, right. I think it will come up somewhere, but let me briefly tell you this. There are flows all over the body. The blood flows, lymph flows, so many things flow in the body. Many flows occur in industries. Okay, the industry thrives on fluids moving from one point to the other for various processing, for producing products, and so on and so forth. So fundamentally, flows are important for us, and that's the reason why we biological engineers are studying this. We're trying to understand so that we can analyze new situations, then design for new things, or even if there are existing situations, we can troubleshoot and then operate things appropriately and so on. Let's move forward. We will start with shell momentum balances. Recall that we did, I think I need to keep changing this, yes. Recall that we have already seen that momentum is a conserved quantity, and therefore momentum balance can be used as a principle to obtain useful relationships. I need to use this, I suppose. On similar lines as shell balance, recall shell balance, we considered a representative shell of the system of interest, and then we did balances over that differential shell. If it is a rectangular Cartesian coordinate system, the shell was a cuboid. If it was a cylindrical system, it was an annular cylinder, and if it was a spherical system, it was an annular sphere, and so on and so forth. So now we are going to do, in the earlier chapter we did mass balances over the shell, and here we are going to do momentum balances. That provides us a lot of insights for analysis, design, and operation. That's our interest in this. As I already said, we are going to do balances over a thin, geometrically representative shell of fluid, and this thin representative shell of fluid will turn out to be the system or the control volume over which the momentum balance is written, and then of course you can integrate it for the entire thing. So to understand the application of the shell balance principle, I am going to consider a certain situation, a reasonably gentle situation. This is the case of flow in a falling film over an inclined surface. You have a surface at an angle, there is a thin film of fluid that is flowing over it, and we are going to consider that case. The flow has practical applications itself. This kind of a situation, inclined flow, it has practical applications. The Bostwick viscometer is essentially this, and that is used to measure viscosities of fluids. That uses the same kind of flow, and by making certain measurements, the viscosity can be calculated. So in the earlier chapter, we balanced mass, as I mentioned. We wrote it as follows in general: the rate of total mass out of the system minus the rate of total mass into the system plus the rate of total mass accumulated in the system equals 0. We said into minus out equals accumulation, I have just transposed the equation here for our purposes. So rate of mass out minus rate of mass in plus rate of total accumulation equals 0. This is accumulation in the system. We know from basic physics that momentum is conserved in the absence of external forces. Rate of change of momentum is directly proportional to the forces acting on it. If there are no forces acting on it, the rate of change of momentum is 0. So when external forces are present, that's what I just mentioned, according to Newton's second law, the rate of change of momentum is equal to the vector sum of forces that act in the direction of motion on the system or the control volume. Okay. Just note, these are very essential things. The vector sum of forces that act in the direction of motion, that is all. The other directions, perpendicular directions especially, we are not bothered, on the system or the control volume. So, on the same lines as the this is used only for a laser pointer. On the same lines as this, rate of total mass out minus rate of total mass in plus the rate of total mass accumulated in the system. Instead of mass, if we use momentum, we get rate of momentum out of the system minus rate of momentum into the system plus rate of momentum accumulation in the system equals the sum of forces acting on the system. Instead of 0 when it, as in the case of mass, here it equals the sum of forces acting on the system, or in the absence of any force acting on the system, it is 0. So, when we say conservation, we are taking the special case of no forces acting on it. It is strictly speaking Newton's second law that we are applying here. This is equation 3.3-1. Under steady state conditions, the accumulation rate is 0. Okay, this term can drop out. So, at steady state, we are imposing the condition of steady state now. We can write this equation as rate of momentum into the system minus rate of momentum out of the system plus sum of forces acting on the system. Essentially, I have taken the two terms to the other side. Sum of forces acting on the system equals 0. Okay, I hope you are able to see this. Just transpose this equation and put this term to 0 because it is steady state. Momentum can enter or exit the shell that we are considering by the following mechanisms: by molecular means, which is through momentum flux, and or through convective means, through fluid motion. Okay, when the fluid is moving, there is a certain velocity, there is a certain mass, so there is a certain momentum associated with the fluid, and therefore, there could be a momentum flux that is caused because of the motion of that fluid, right. So, that also will play a role in this momentum equation. That is a contributor to the momentum here. So, we need to take that into account. So, let us rewrite this in terms of the quantities that are convenient to us. This is fine, this is in principle, this is generally valid, but none of these we can directly measure, we will have to measure separate things. So, we will write it directly in terms of measurable variables. So, this is the situation that I have been talking about. Let me give you some more details. We have an inclined plane here, we have a fluid flowing over it, which is given here. This is a very thin layer of fluid, I have just expanded it here. And let us say when it starts flowing in this region, you will have some entrance effects and so on and so forth, some non-idealities. Here when it is moving out, it will have some exit effects. We will analyze the flow when these things do not bother us. Okay, that will be for most of the flow essentially, only exit, entrance and exit. As long as we do not measure things there, we are fine. So, let us take a section of this flow of length L, and this is a section that we are going to analyze. And in this section, the flow is well developed, and therefore, Vz, this is the z direction here. Okay, this is the z direction here. Vz is not a function of z. Okay, it has already achieved well developed flow conditions. Nothing is going to change with the distance here at a particular point away from the plate. The velocity here will be equal to the velocity here. That is called well developed flow conditions. That is what we are going to take. I will come to the pressure in a little bit, and this is of course at an angle of beta. The plate is at an angle of beta. This Vz is not a function of z, is well developed flow conditions which exists. So, it is not an ideality or anything like that, it actually exists. So, a slightly different diagram to understand the momentum flows a little better. This is the thin plate here. This is the fluid that is flowing over a plate. This is the shell, the hashed area, this hashed thing that I have shown here is the shell that I am going to consider, a cuboidal shell. So, it will be a rectangle in a cross sectional view. There is this dimension into the board that I am into the screen that I am not going to consider here, because there is no variation across that distance, and therefore, 2 dimensions are good enough for us to get a complete picture of this. So, this is the shell here. The shell is of a thickness delta x. X is this direction, okay, here it's given here, x is this direction, z is the direction of flow here. So, if this is the 0 point that we are going to consider for analysis, the shell is located at a distance of x and has a thickness of delta x. So, there could be momentum transfer through viscous transfer. Viscous is, we said that one layer of fluid moving affects the other layer and so on and so forth by the viscosity, by the shear stress and so on and so forth, right. That is what we mean by viscous transfer. This was the case of the first situation where we had 2 parallel plates and 1 plate moving. Similar thing happens in all these situations. So, there could be momentum transfer in the x direction by viscous transfer, and there is of course fluid moving in the z direction. Therefore, the momentum transfer into and out of this system, the shell, would happen by flow. It comes in by flow here and goes out by flow here. So, this is the second component. This is by viscous transfer and this is by flow. And width of the film in the y direction, which is this, is W. This is the direction of gravity, and you have your angle here indicated, and the length of this section is L. We are interested in knowing what is the velocity distribution with or the velocity variation with the depth of the thin fluid that is flowing. That insight we want, and also we want the shear stress distribution. Okay, these two are very important insights that we can get from flow situations, which will help us in a variety of ways, and that is the reason why we are focusing on this. So, the velocity distribution, shear stress distribution is a very standard thing that we look for whenever we analyze flow situations. Note tau x z. X is the direction of action in this direction, z is the direction of motion. So, this picture you need to keep on making till you become comfortable with it, and then it will become second nature to you. Also note, the rate of momentum is nothing but area times momentum flux. The same way mass rate is mass flux times the area. You multiply by the area by the momentum flux, we get the rate of momentum. And each term in that momentum balance was rate of momentum. Now, we are going to express the various terms in the momentum balance in terms of convenient quantities, measurable ultimately maybe. So, by molecular mechanism, by the viscous effects, the rate of z momentum n across the surface at x. Okay, let me show this to you. The rate of x momentum n across the surface at x. This is what we are looking at. See, this is our system. We are doing balances over the system. We are looking at how momentum moves in and out. So, the momentum by viscous transfer will move in here and move out here. So, the rate of z momentum n, because it is caused by the motion in the z direction, the effect is in the x direction, but this is because of the motion in the z direction, we call it z momentum. The rate of z momentum n across the surface at x is nothing but the momentum flux times the area. Momentum flux tau x z at x, that is straightforward now. The length is the length of the plate for analysis, W is the width. So, therefore, that will give you the area. So, area times the momentum flux is the momentum rate at n across the surface at x. The rate of momentum, z momentum out across the surface at x plus delta x, which is here. This is the surface that we are looking at. This is x direction, x here, x plus delta x here. Okay, is nothing but the shear stress tau x z at x plus delta x times the area. Area remains the same. By convection, by bulk motion, by the fluid motion, there is another component to momentum in this case. So, rate of z momentum n across the surface at z equals 0. You need to understand this better. So, let us get back to that figure. See, z equals 0 is what? This here. Okay. So, flow is occurring here. The system is limited to this now. Therefore, flow is occurring here. So, rate of z momentum n, the momentum in the z direction, and this is the phase across which it enters, this is the phase across which it leaves. The phase at z and the phase at L, z equals L, z equals 0 and z equals L. The rate of z momentum n across the surface at z equals 0 is, let us write it like this, rho Vx, okay, some momentum you can understand, times another Vx here, and this is the area. So, W is this times delta x is this, therefore, it will give you the area of this phase through which it is coming in. Fine, that is the area of the relevant, that is a relevant phase for us now. The motion is in this direction. So, W times delta x is straightforward. Let us try to understand this a little better. Of course, rho Vx at z equals 0. We write it in this way to facilitate us later. So, let us keep this same thing. I will show you how this becomes momentum rate. Rho Vx. Okay, rho Vx is nothing but density times the velocity. So, density is mass per unit volume, m L by L cubed. Velocity is L by T. Let us just consider this Vx alone for now, multiply it by L by T. This is the area, okay, we will bring it in later. This can be rearranged as m, we will take 1 L by T here and we will take the 1 by T along with this, and what remains is these two L's we have not, one of the L's we have not accounted for. So, L remains here and the L cube comes here. Okay. So, what is this? This is momentum rate times the L by L cubed is L 1 by L squared. Therefore, we need to multiply it by L squared to get momentum rate. So, this is momentum, mass into velocity is momentum rate 1 by time, momentum rate, the way we have written it, it has an L by L cubed which is 1 by L squared. Therefore, we need to multiply it by the area here to get momentum rate. I hope that is clear. Once that becomes clear, if it is not clear, just be with it, pause the video here, just try to understand this and then move forward. It is very essential to understand this. We will be using this again and again and again in a lot of formulations, a lot of derivations. Now, the rate of z momentum out across the phase at z plus z equals L. Okay, I think I showed you that. Let me show it to you once more maybe. Here it is moving out at the phase z equals L. Equals in the same format W delta x V z rho V z at z equals L. Good. Now, let us consider, we need the forces, right. We have the input and output terms, fine, the momentum in the momentum balance, right, the rate of momentum into the system, rate of momentum out of the system. We have this third term here, sum of forces. We have accounted for this and this, we need to account for this in the momentum balance. We are just filling in the terms here, then we are done. To account for the forces, let us draw a free body diagram. how we are doing. Okay, we are fine. Let's take a break just after this maybe. So, free body diagram here, this is the shell, right, of fluid that we are considering. Therefore, this is x, this is x plus delta x, z equals 0, z equals L. There is, we have cut out the shell from the fluid. The free body diagram shows the forces that are acting. There will be a pressure force that is acting in this direction, and therefore, W times delta x is the area times the P0 pressure. This gives you the force in this direction. There is another force, the pressure force that is acting in this direction. W times delta x is the area times PL, the pressure here is PL, that is this force. And then of course, there is a normal force here N. There is of course a gravitational force here, which is mass rho times V. Rho is the density times the volume of this times the acceleration due to gravity. And of course, this is at an angle of beta to the vertical. Okay. So, these are the various forces that are acting. However, note that this Z is the direction of motion, and we are only worried about the forces in the direction of motion for us to do a momentum balance, or to consider how the movement in that direction is affected by the forces. So, we are worried only about the components in the Z direction. Also note that the liquid layer is open to the atmosphere, right. It is a thin layer with negligible vertical distance. Okay, I already said it is a very thin layer. That is the way the Bostwick-Wisk commutator works, by the way. It is a thin layer with negligible vertical distance. Now note, when the liquid is open to the atmosphere, the pressure at the top surface is going to be that of the atmospheric pressure, and the layer is very thin. Therefore, there is the hydrostatic pressure because of that thickness of fluid can be neglected. Okay, that is the reason, that is one of the simplifications that we have, because it is a very thin layer. And therefore, the difference between this pressure and this pressure can be considered negligible, or in other words, P0 can be taken to be the same as PL in this particular case, because the layer of fluid is very thin. And because of that, this force will cancel with this force. However, and of course, the normal force is not in the is in the perpendicular direction to the direction of motion. Therefore, this will not contribute. However, there is a gravitational force here, and there will be a component in the direction of motion that will contribute. So, normal force is not relevant because of the direction being normal or perpendicular to the direction of motion. In this case, we are ignoring the force due to pressure difference because the film is thin. I have already told you this, and therefore, the gravity force is the only significant one. If other forces are present, let us say some electrical force is present, some mechanical force, some magnetic force is present, some other forces are present, this is the place to include them. So, this analysis considers only these forces: normal force, gravitational force, the pressure forces which you have neglected because of the thin film, and so on and so forth. In addition to this, if there are other forces, then you need to include that for your situation. Gravity force acting on the fluid in the direction of motion is going to be the component of this in this direction. This cos beta is the going to be the component, you all know that. Therefore, the mass mg cos beta, the mass is Lw area times delta x. Therefore, that gives you the volume of this fluid being considered. Volume times density is mass. So, this gives you mass mg cos beta, straightforward. Okay. Now, if we substitute back into the momentum balance, input output forces. So, the input due to the molecular term across the x and x plus delta x, input here minus output here. This is due to the bulk motion moving in, moving out. Okay. w delta x rho vz squared z equals 0 minus w delta x rho vz squared at z equals L. And as we saw, the force, sum of the forces came down to only the component of the gravitational force, L w delta x rho g cos beta. So, all this put together is 0. That is nothing but momentum balance. Okay. So, we took the second law of motion, momentum balance, and then we have just filled in the terms. That is all we have done. Only thing is that we have filled in the terms in terms of variables that we are comfortable with. Let us call this equation 3.3-2. We are analyzing the situation when the velocity in the z direction is not a function of z, and therefore, these two terms are the same. So, the third and fourth terms will cancel. Now, if we divide throughout by Lw delta x and take the limit as delta x tends to 0. Why don't you do that? Why don't you pause the video here, do that and tell me what you get. Same scheme as some of the earlier things that we have done. So, it must be familiar by now. Why don't you do that practice? Let me know. Pause. Go ahead, please. If you did that, you would find that we are dividing by Lw delta x and then taking the limit. Therefore, what we have here is tau zx at x plus delta x minus this, because there will be a negative term here. I have taken this to the other side. Therefore, tau zx at x plus delta x minus tau xz at x plus delta x minus tau xz at x divided by delta x in the limit that delta x tends to 0 is rho g cos beta here. Okay. Or d dx, this is nothing but the definition of the derivative. D dx of tau xz is rho g cos beta, equation 3.3-3. So, if we solve this, we directly get the shear stress profile. So, it is first order differential equation. The solution is quite straightforward. Here just one integration, rho g cos beta times x plus the constant of integration. To find the constant of integration, before that let us call this equation 3.3-4. To find the constant of integration, we need boundary conditions. So, what is the boundary condition here? Please pay some close attention, because this boundary condition we are going to use again and again and again. At x equals 0, which is the surface of the liquid, the gas liquid interface, okay, the liquid layer is moving and there is air above it, liquid gas interface. The layer of air that is in close contact with the fluid will also move at the same velocity as that of the fluid under no slip conditions, okay, or let us say, this is air, so it doesn't really matter. So, there is a fluid moving, there is a topmost layer, and the layer of air, the layer of gas above it will also be pulled along at the same velocity, okay, and this is the condition at the gas liquid interface. When this happens, there is no velocity gradient there is no change in velocity with respect to distance, and therefore, there is no momentum flux at x equals 0. The momentum flux at x equals 0 is 0. Momentum flux, as we all know, is shear rate, and shear rate is proportional to the velocity gradient. If the velocity gradient is 0, the shear rate is 0, and therefore, the momentum flux is 0. So, this is the boundary condition, a very important boundary condition, and the standard boundary condition that can be used at the liquid gas interfaces throughout is that the momentum flux, hence the velocity gradient in the liquid phase, can be assumed to be 0 for most calculations. So, at x equals 0, tau x z is 0, equation 3.3-5, and this boundary condition applied onto the solution yields C1 equals 0, that you can find out yourself, and therefore, you get tau x z equals rho g x cos beta. So, we have an expression for the shear stress in the fluid. We are drawing insights into the fluid flow behavior. We have an expression, this is a function of x. So, if you visualize, this is equation 3.3-6, The shear stress distribution is known from this. If you visualize, you see it is varying from 0 value to a maximum value. It's a linear variation here. X is a linear function, rho g cos beta times x. So it's a linear variation from the value of 0 to some maximum value at the solid surface over which it is flowing. Okay. So we have the shear stress distribution. We said we look for shear stress distribution and velocity distribution. When we meet in the next class, we have been at this for some time. So when we meet in the next class, we'll look at the velocity distribution. We are drawing insights into what's actually happening. And those insights are going to be very useful in design of new things, in understanding old things, even operation and so on and so forth. That's the reason why we are doing this. The initial, perception of some students is, what's the point in knowing about velocities? Let they be whatever they are. What's the point about knowing the shear stress distributions? As you'll see here, these give you how the fluid behaves. The fluid behaves determines so many different things. Suppose you want to carry out certain things in a miniature level. The flows will be microflows. Do you get the same level of mixing that is required when you convert a flow from a normal situation to a microflow? That's a question that you need to answer if you're going to design such microflows. And to design that, you need to understand how the flow is happening, how the velocity behaves, how the shear stress behaves, and so on and so forth. That is the kind of insight that you're getting here. Okay, and that's the reason why we need to understand this better. Let's meet in the next class and take things forward. See you then.